Hi, everyone. Thanks for showing up. First of all, I wanted to say, if you have questions for me, feel free to interrupt me. I'm happy to have a conversation about this. If you have general questions about C++, there's a good chance that there's someone in the chat who can answer them for you, but that always seems to happen. Questions posed in the chat get answered pretty quickly, but we can also, answer out loud or talk. So just if any questions get posed in chat and no one says them out loud or could answer them, if they're directly for me, could someone speak up and read them to me? That'd be great, because I won't be watching. Okay, so today we're going to be talking about C++20's views from the perspective of creating a new one for ourselves. So this is an extension of my lightning talk from December. So for those who saw that, you'll recognize some of the beginning material. But I'm going to be going into much greater depth on some of the common problems that you may encounter if you're creating a view for yourself, and some of the general C++20 changes that make views possible. So these are some views from C++20. They let us write this really nice, clean, composable, lazily evaluated code for common problems, and they're probably my favorite part of the new standard. There are a lot of cool features, and we can discuss that later. But as a library person, I'm most interested in how they work. How would I go about writing one for myself, and how do I learn enough to make that happen? So as always, learning is best with an example. So this is my little toy project where I'm playing around with orbits in a solar system and predicting the orbits based on, inside of the Unreal Engine editor, which is pretty handy. These are the concepts which I'm using for that. So I just have a gravitational body, something with mass, location, and velocity, and a gravitational range, which is just some collection of gravitational bodies. And then I have this predicted body state, which is really a point on those predicted lines, right? So this is the location and velocity that one of those planets is going to have in the future. And by connecting all of those points, I can create that trajectory. Here is a slightly messy single step of the prediction code, which is called each time we need to generate a predicted state of the universe. So you call this many times with a small delta time and connect all of those predicted locations in the editor, and that draws the orbital predictions. So you can see our future states is a vector of a state, which is really just a collection of those predicted bodies, one for each planet that we have. And we call update gravity in there during our transform. So let's take a look at that, how that looks for the red planet specifically. So if we pass in the red planet and we pass in the list of all of our planets, we use that to calculate the force, and then from there we get acceleration, velocity, and location. Easy enough. We're not worrying about anything like interpolation here, which would get a much better view of where things would go. We're just trying to do this quickly. And so then this is get force on body. And this is also kind of messy, but this is what I want to address. Okay. So at the bottom, you can see we're doing a transform reduce, and we're taking all of the planets that we have, and we are transforming them into the force that they are exerting on the one that we're looking at, in this case, the red planet, and then we are summing all of those together. And you can see in our single force on this body, we run into the red planet in the list of all of the planets, and we just decide that it doesn't exert any force on itself. It's easy enough, but it's kind of annoying. I don't really like this line. This is a bit of a code smell because it means that my structure is wrong. I'm not looking at my data in the way that it should be. I have this special case every single time I run into it. Instead, what I would like to do is to take my collection of gravitational bodies and see it as groups of pairs so that I can easily see each body paired with everything that exerts a force on it. So there are a lot of ways of doing this, obviously. One option would be to use a regular old transform and create the new collection on the right, but that would grow way too fast. If we have an input set of n elements, the output is n squared minus n. So if we added an asteroid belt, we'd run out of RAM, basically. Using manual loops to do this is hard to parallelize, so I use algorithms, but that has the problem that we encountered. It's just not the right view of our data. It still doesn't have all that much control. It's weird. So instead, I'd like to represent my collection in this new way as a new collection, but I want to do it in a way that I don't run out of RAM. And I can achieve that with a C++20 view. So first things first, what is a view? During this talk, I'm going to be mentioning range v3 a lot. And Eric Niebler was one of the many people who worked on C++20's ranges, but his range v3 library houses the original implementations for a lot of things in ranges, like std views. So this includes, his library includes a lot more views than are in the C++20 standard, so hopefully we'll see more of them adopted in the future. There were a lot of other authors of the one ranges proposal. I think it was also authored by Casey Carter and Christopher DiBella. But today's topic is much more focused on Niebler's contributions. So let's disambiguate a little, because these terms are both introduced in C++20, and no one really talks about the differences or how they're related. So I want to just be very clear. Ranges aren't a new thing. It's just a generalization of the old thing. So it's any collection of things, and syntactically it's anything with a begin and end function, right? So obviously standard containers like vector are a range. Views are also a range, but these are a new type of range which are introduced. And most importantly, unlike all of the standard containers, they're constant time everything. You can use them in this very light way without worrying about how many objects they represent. And because they're lazily evaluated, we can even have them representing an infinite number of objects, and it's still just a little class that's easy to copy around. You may also see the terms range adapter and range factory. So in the spirit of disambiguation, let's clarify this one as well. So a range adapter is a class, a type, which is responsible for taking a range as an input parameter and producing a view. Most views in the standard are made by adapters. So, and adapters can also compose into other adapters. So A and B in this slide, on the left side of the slide, are both adapter types. They are copies of instances of adapters. So reverse is an adapter. It's not a view, it's an adapter. A range factory is a view which creates elements from nothing, more or less. It's usually used as the source of a pipeline. You can't pipe something into it. And there are only 4 of them in the standard. So I mentioned iota view, which is, in this case, it represents all of the integers from 1 to 10. There's iStream view, which allows you to turn a thing like string into a range, which you can pipe in, input streams for strings, excuse me. So those are very handy. And then there's also empty view, which is a range of 0 elements, and single view, which is a range of 1 element. So those aren't really worth putting on the slide. So we're going to be focusing mostly on the left column, on range adapters during this. Range factories are very interesting, but I don't have as much experience with them. A lot of this will cover both of them, but that's a topic for another talk, I'm sure. Also, really quick, just a nice little thing in the standard that I want everyone to be aware of. If you're using the namespace views, you don't have to go through ranges first. It just makes everything easier to read. So one last definition, which is not so much standard as useful and generally applicable. Views can be composed together, adapters, excuse me. I should say adapters can be composed together using the pipe operator, right? A series of multiple composed adapters is often called a pipeline. So this thing, which is highlighted in this code, might be called a pipeline. And to be complete, it needs source data. In this case, iota. This is, all of the integers starting at 2. So this is a term that I will be using and I've actually used already. I just wanted to be clear on what that means. All right, back to the example. I'm going to be referring to the group of yellow paired with everything else, that bracketed section, as the inner view, and iteration across those as the outer iterator. So here is a high-level description of the new view. If you saw my lightning talk, I want to point out that this line is somewhat different because it was wrong originally. I implemented it wrong. So you kind of have to be careful with what types your view is defined for. Also, 2 more terms, I suppose. I'm going to be using these terms in discussing the inner types. Parent refers to the all pairs view that created the inner type, and base refers to the view that was piped into this one in a pipeline. So keep those in mind. This base term is not mine. This is common in the views library. The parent is mine, and maybe it could have been more specific. So this line is hiding a lot. And in fact, all of the interesting work in this view can be hidden by this line. And so my general takeaway from this whole endeavor is that a view is usually just a supplier of a fancy iterator. So that's certainly true in this case. I'm going to break up the types because I have an outer iterator and inner types. And so we're going to first take a look at the inner iterator, which is the one that's providing a pair of, for example, the sun paired with the red planet. These are the types that are defined on my inner iterator type. So you can see my use of that term base, where the base iterator is the iterator type that was piped into us. And then I have the 5 standard types that you have to define for an iterator, and I'll come back to these. But you can see that I have a value type of pairs of the base value type. So for a base value type of planet, my value type is pairs of planets. Same with reference. I have pairs of references. Note that constness is not yet fully complete. We need to be more rigorous in determining whether we have const references to underlying planets or whatever, but that can come later. That's a common problem in iterators, not unique to views. Also, I'm just doing a forward iterator, and there's a reason for that that lends itself to slide code. But this could definitely be random access. These are the members that are defined in inner iterator. So it has 3 component iterators and 1 private method, and then some standard stuff that you'll see in a forward iterator. This private method is basically the logic that I didn't like before, but now it's in library code, so it's better. So this is where we decide that we have a pair of matching elements, so we want to skip. So I need to do this every time I increment the inner iterator. It's not the best solution, but that's trivial. All right, here are the constructors and the dereference operator. So you can see we are always constructing the inner iterator, the innermost current inner, as the beginning of the base. So my inner view is always starting at the beginning, which is a little bit weird, and we'll see why later. Our dereference operator is returning, as we said, pairs. So we're dereferencing the 2 iterators that we're pointing at, and that's what we return. Then we have our operator plus plus. The prefix is not all that interesting, and then postfix is always implemented the same way, basically. I like to mark my postfix operators as no discard, because if you're doing a postfix increment, you're just wasting time if you're not saving that value. And then operator equal equal. As of C++20, operator not equal is auto-generated for you, so you don't have to do that again. That's nice. Since my iterators are defining this in a well-ordered sequence, I could certainly supply less than and greater than, but in which case I would just do the spaceship operator, but for now, this is fine. This is sufficient to be a forward iterator.
You don't have to explicitly default the not equals, that's implicitly...
Yeah, it's implicitly defined even if you don't default it.
Okay, cool.
Yeah. And actually in the next type, we'll see even more stuff is implicitly defined for you. So the next type is the sentinel. So we're going to talk a little bit about what sentinels are and why you use them. But here's my sentinel definition, and it looks a little funny if you haven't seen a sentinel before, or even if you have. But the second call there is equality operator with the inner iterator. And this is really the job of a sentinel. But as of C++20, the compiler uses that call to generate the not equal operator and then also flip the arguments. So you no longer have to do 4 free functions for this kind of thing. You can do 1 member function and you get them all for free, which is pretty cool. Okay, so this line is especially weird looking if you don't know anything about sentinels, or even if you do. So let's talk about sentinels for a bit. So we're all familiar with a sentinel value, like the null character in a string, right? A sentinel value is just a specific value of the same type as the rest of the range, which indicates that you've reached the end. A sentinel type is a new thing in C++20, in the ranges part of the STL. The rest of the STL doesn't really support sentinel types, but the ranges namespace does. And it's just a small class returned by the end calls, so it's potentially a different type than the iterator returned by begin. And its sole job is really to check equality with the iterator type, okay? So this is the concept. A class S is a sentinel for a class I if S is semi-regular, and again, that's copyable and default constructible. I put it on the slide, but I didn't point that out earlier. So semi-regular is like kind of like an int, right? It's easy to use. It's lightweight, small. That's how you generally think about it. I has to be some kind of iterator of the weakest value category. And then they're equality comparable. This is an exposition-only concept. It doesn't really matter the details for our purposes right now, but you can look those up if you want to on your own time. So the semantic requirements, this is what CPP reference gives us. The second point is the interesting one, which is in defining a sentinel. So if I is not equal to S, if an iterator is not equal to a sentinel, then I is dereferenceable. And if you increment it, it's still part of a range, okay? So this is what's really giving us the validity of I. As long as that's the case, I is a valid iterator inside of our range. This highlighted line is a convention. It's not required. If sentinels are comparable to themselves, and they don't really have to be, they're generally just considered equal, even if they're from different ranges. But that still doesn't answer the question, why did I use a sentinel instead of a proper end iterator? So let's talk about that. And first, we're going to look at vector. So for vector, it's really easy to decide when we're at the end, right? We can do pointer arithmetic because vectors, iterators are just pointers, really. So if we are n elements past the beginning, we're at the end. It's that simple. For all pairs view, things get a little bit harder. The end of the inner view is a pair of something combined with an end iterator. And there are actually several ways of calling it the end. In this case, there are 5 ways of being an end iterator for the inner view. For the outer view, it's the end iterator deterministically paired with the 0th element of the input, which is weird. There's this potential sentinel value that you might use, but we don't actually use that anywhere, of just 2 end iterators, but that doesn't appear. One of the shortcomings with my design is that you can't construct this end of inner pair just out of nowhere. So the inner iterator is always constructed as pointing at the first element of the input set, and there's no real way of jumping past that. We could add that support, absolutely, but doing so would complicate the interface with a new constructor only so that we could construct an end iterator. If I added random access support, I would rethink this, right? We can already jump anywhere, so let's jump to the end. But for a forward iterator, we can't jump to the end. And so adding that interface would just complicate the class unnecessarily. So my general reasoning for using a sentinel is that sentinels separate concerns. Any non-trivial end logic has its own class, and it allows us to have this nice decoupling between the iterator's job and what it means to be at the end of a sequence, which shouldn't really be defined inside of the iterator. So pretty quickly after starting in C++20, I find that I really enjoy reading sentinel code more than 2 iterators, if possible. So that's the sentinel. And then to conclude the inner stuff, here's the inner view. Okay, I skipped over it, I guess. Okay, here's the inner view. So this is a proper view. It inherits from view interface, same as all pairs view does. And all it does is begin and end. It returns the iterator type for the begin and the empty, easy sentinel type for the end. And that's all it takes. And as we've seen, all of the logic was in the iterator, right? This is a view, but all of the work went into the iterator. So there you go. Are there any questions before I continue on? Okay. So on to the outer iterator, which is pretty straightforward. Definitely easier than the inner one. But, so here we define, this is the first half of the outer iterator implementation, and we define our 5 normal types for an iterator. And they look weird, but I'm going to come back to this because I'll just show the rest of this. So yeah, we have a pretty normal constructor. We have our dereference operator, which is returning an R value of type inner view, which we're constructing. Kind of weird. Our prefix operator, you have to have postfix to be an iterator, but it's easy. And then our equality operator. Also, this sanity check is a good idea when you're developing. I accidentally left the const off the operator star, and it helped me figure this out. So that's always handy. Okay, back to this. Why is the reference type equal to the value type? And if that makes sense to you, why is there a pointer type? Because you saw in our dereference operator, we're returning an R value. So who is taking a pointer? Like, what are they pointing at if they're using the pointer type? So why do we have these things? So again, for a vector, if a vector has a value type of planet, its reference type is planet ref. That's easy. They're pointing at the same objects in memory. For the all pairs view, on the inner side, a value type of pair of planets, it's not a reference type, which is a pair reference. It's a pair of references, but that's still fairly straightforward, right? That makes some kind of sense because you still have access to the underlying elements through that. But for outer iterator, a value type of inner view, which is an R value, what would its reference be pointing at? You know, that doesn't make any sense. So in order to investigate these weird types on the outer iterator, as well as the weird reference type on the inner iterator, which is a slightly different but equally problematic type, let's take a step back into less complicated and much older example of the same problem. Vector bool. So I'm sure many of you are familiar with the issues caused by the vector of bool specialization. It's an old problem, which has been around for as long as the STL. But what I really want to look at is how C++20 fixes many of those issues. But first, let's describe the issues. So this is the description of vector of bool from CPP reference. And if we highlight the important stuff, we can see vector of bool is space efficient by not necessarily storing its elements as a contiguous array and exposing a class, stood vector of bool reference, as a method for accessing individual bits. So what that means is we have a vector of booleans, and instead of storing it as separate bytes, all of which only use 1 bit, we pack all of the bits together into a single byte, which is great because we still have half of a byte to use before we need another byte. So we have all this room. But unfortunately, it means that instead of having all of these nice types defined like stood vector has, so like const reference is a const value type ref, vector of bool looks like this. Everything is implementation defined. Our const reference is just a bool by value, which is weird. And our reference is a proxy class representing a reference to a single bool. So this has all been in the standard for a long time. It was addressed in this paper by Herb Sutter in '99. So this is nearing, 22 years old now? It's an old problem. And in this example, or in his paper, he showed this example where you're writing generic code and you couldn't constrain it with concepts back then, but you take in some type T, and presumably to get it to compile, T has a value type, and you want a pointer to the first element of T. And this would compile for every vector that you pass in, even vector of bool. But as we've just seen, there's no byte that holds the bool that you're looking at. So what are you taking a pointer to? This is a pointer to a temporary, and it's invalid code. But it wasn't caught at compile time. So what do we do about this? Well, for starters, don't write code like this. I mean, that's not generic enough. So let's be a little bit more generic. Write code expecting proxies, and we'll define that term in a second, but that's still not general enough. Write code that conforms. Okay, that's too general and a little bit too harsh, because before C++20, that was not really possible. So let's go over this term proxy and see why that is. And if you're interested in more about this, the P0022, which introduced the proxy iterator requirements to the ranges library, has most of this content. So a proxy reference or a proxy type, maybe even a proxy class, is a type that acts like a reference for another type, even when it's an R value, okay? We've seen this, it makes some amount of sense. A proxy iterator is an iterator whose reference type is a proxy reference, okay? I'm gonna use proxy iterator more often, probably. Some examples of that, vector of bools iterator, obviously. Dereferencing it may return an R value of the type, some type named reference, and reference provides read and sometimes write operations to the underlying bits. If you had a vector of const bools, you don't get the write operations, but that's what it does. The all pairs view inner iterator. Dereferencing this one returns an R value of type pair of references, right? And pair, just like reference in vector of bool, provides read and write operations to the underlying values. So seeing things like this, where our reference type isn't a reference type, might make you wonder, are proxy iterators even allowed? Is this something that we can do? Yes, you can, only as of recently. So with C++20, we get some much more generous guidelines for how iterators should look, and proxy iterators are fully and officially recognized and supported. Before C++20, this is a named requirement expressed as a concept, but this is how a forward iterator was defined before C++20. So a legacy forward iterator, it was an input iterator, and it was several things, but most importantly, its reference type was an actual L value reference. So you may realize that that means vector of bools iterator is not an iterator before C++20. Post C++20, everything's much simpler. To be a forward iterator, we're just these four things. We are an input iterator, we're tagged as a forward iterator or better, we're incrementable, and a sentinel for ourselves. Also, remember how the outer iterator had this pointer type? Even though its references were and its values were always R values, I was doing this because before C++20, all 5 of these types were required in order for something to be considered an iterator. So this is an excerpt of how iterator traits would have been defined before C++20. All 5 types are used with sphenae to define this struct, and this is used in defining whether something qualifies as an iterator. This is how it looks now, using concepts instead of sphenae, but the pointer type is defined as void if the iterator doesn't define it, which is exactly what we want for the outer iterator. So it still supports the legacy iterator stuff, but it works perfectly for proxy reference types. So also remember the legacy iterator requirements. This uses iterator traits to check this value. So even though legacy input iterator didn't need an L value reference type, it still needed a pointer type. So thank goodness that requirement is gone. So I took out the pointer type. That doesn't have to be in there. I put it in by habit and as a placeholder until I figured all this out. But in researching further, I realized I didn't need it. So this is another reason to use that static assert with concepts for sanity checks. After removing the pointer type, this still compiled, so I was good to go. Okay, quick step back, because that was a whole bunch of different things at once. Basically, all it was saying was that before C++20, vector of bools iterator wasn't an iterator. But as of C++20, you're allowed to have proxy references. Vector of bool is fixed, kind of, mostly fixed. But a lot of other things had to change in order for proxy iterators to work. So we fixed the expectation for references to be actual L value references. What other things had to change to make proxies a full member of the standard? Customization point objects are a big one. They're not strictly required, but they use a common pattern in std ranges, so I wanted to talk about them first. So previously in C++ 17 and before, customization points like begin, end, and swap were pretty awkward to use. You see here that I am using std begin and std end, and then I'm calling unqualified begin and end, and hoping that I get the right version. This is using something called argument dependent lookup, ADL, which if you aren't familiar, there are some great talks talking about why relying on ADL is problematic often. So a couple by Titus Winters come to mind. I definitely recommend watching that if you don't know much about it, but I'm not going to go into it too much. But this is especially important for swap, because if you defined your own version of swap for your object, then you want that version to be used. You can't use the standard swap. So they're a pain to use. There were only a couple of them. There were things like std hash, which are customization, but they're an explicit specialization of a template, right? So there were only I think these are the only three that I could think of, which were customization points. They were much easier to get wrong than to get right. This code looks like it's fine, and it probably is, because your container probably defines a dot begin and a dot end, but it's not technically supposed to be called this way, right? You're supposed to allow customization, and it's especially the case, again, with swap. Calling std swap seems fine, but it wasn't. So moving forward in the standard, I believe that this is generally the idea moving forward. We're going to be using semi-regular objects that do the ADL for you, okay? So std ranges begin is an object of an unspecified type, and it has a parentheses operator on it. So you can take a copy of std ranges begin and pass it around if you want. This is a common pattern with all of the new ranges features, and we'll see more about it when we look into writing our own custom range adapter for the all pairs view. So this is now the correct way of doing it. You don't have to do any of that ADL nonsense because ranges begin does it for you. It's the same with ranges swap, by the way. So always use that. Don't use std swap anymore. Okay, iter swap. So this is another problem that we had to fix. This is some really bad slide code where I'm trying to swap the values pointed to by two different iterators, and I'm even doing the right ADL thing, right? So this is great. The problem is, if I got a proxy reference type, then the dereference operator returned two R values. I swapped R values. My container is the same as it used to be, and my code is broken. So this doesn't work for proxy types. So iter swap existed in C++ 98, but it wasn't really a customization point. In fact, the standard didn't require that algorithms do that ADL trick. So a lot of standard algorithms like std reverse simply called the qualified std swap, or std iter swap, excuse me. So that doesn't allow us to customize iter swap or to use them with our custom iterators. So that's not very helpful. So the std ranges version accounts for that, and it'll always use your version if you can. And your code should always use it too. If you're going to be swapping elements or moving elements around in a container, you got to do this. That said, you shouldn't have to customize this for your iterator types. Instead, you would customize iter move, which is what we're going to look at next. So this is another bad slide code example where I want to extract a value and leave the value inside of iter in some, undefined state. But again, I got a proxy reference type as an R value, so I moved an R value, my container is the same, and my code is broken. So std ranges iter swap, or iter move, excuse me. Iter move didn't exist before. It didn't come along with std move. I'm not sure why. I think it was just an oversight. But it's another customization point specifically for proxy iterators, and it's used by all of the std ranges algorithms where it should be. It didn't affect any of the old algorithms, though, so they're still going to be using move. So if you have proxy iterators, You basically can't use any of the old algorithms. You have to use the stood ranges algorithms. So think of this as move a value out of an iterator and it returns an R value type. It's not an iterator type. It's not associated with the iterator. It's an R value of the value type. So stood move won't work for your iterators. You have to customize this, and customizing it gives you iter swap for free. Okay. So a lot of people talk about customizing it, but what does it mean to customize iter move? I want to take a quick look at that. Well, it's obvious, isn't it? This is the CPP reference, how iter move works. And the first point is the one we're interested in, but to be honest with you, I don't understand that first bullet point. I don't know, it's just not, it's not clear. So let me make it clear. Define a function in the same namespace as your iterator called iter move that accepts your iterator. That's it. If you don't do that, it'll just use stood move, probably. So, Jason, are you trying to talk?
Yeah, I'm sorry, probably?
Yeah, there are a lot of particularities in the rules. Those rules spell it out very well. But
Okay.
stood move might not work for your type, so it would just be a forward, that kind of thing. So yeah, my simplified version cut out a lot of detail, surprisingly enough.
Yeah, I mean, I thought I was following along until you said probably, and then I thought I would ask.
Yeah, so yeah.
Okay, that's fine, don't worry about it, yeah.
If there was a general case that would accept your iterator in the same namespace, it might call that one, or there are a bunch of ways that it could still go wrong. But if you're being particular about using your iterator in the same namespace, then you're good. So this is the inner iterator. And this, I just made a friend function because that's the easiest way of doing this. So this is all it takes. And then I get iter move and iter swap. So you can see I'm getting my base R value reference type by just whatever the return type of that iter move is for the two iterators that I have. And then I'm iter moving from them. So I'm basically moving the planet out of that iterator and putting it into my pair of R values and then returning that pair, okay? If you're okay with class template argument deduction, this is sufficient. There are reasons not to be, but it does make slide code nicer. So two things to point out about this. I'm taking the iterator by value here, which is fine because you're semantically moving the thing out of the iterator, right? It's just like a pointer. You don't take pointer by reference. That would be crazy. The other thing here, auto. This is a very useful auto because it allows me to just define a type in well, in this case, 4 lines, but really 1 line in 1 return statement. This is defining my iterator's R value type. So we're going to look at that. On this last line here, iter R value reference T is defined as whatever is returned by iter move for my iterator type. So that's it. So by using auto, I haven't had to repeat myself like with value type and difference type. I've had to declare those specifically, even though, sometimes it can be implicit. Reference type still has to be declared, but iter reference T doesn't actually use that type. It just uses whatever is returned by your dereference operator. But that's why I used the auto there. It's especially useful. And all of these things are also new in C++20, these little helper types. They're pretty straightforward.
Is this underscore referenceable where you're having to kind of peek behind the curtain like you were having to for your...
No. Yeah, this is an exposition. Sorry. Yeah, this is an exposition only concept, which is defined by the standard, but not publicly accessible. So this is basically referenceable means not void. It's basically any type that isn't void, I think. But it's a little bit more specific about it. So it's an exposition only concept that we don't really get to use. I don't know how it's defined.
Are also not referenceable.
What was that?
Bit fields are also not referenceable.
Oh, okay. Yeah, that makes sense. So yeah, that's what that is. All right, there's one more piece that was added to C++20, and it's stood common reference. So we have a problem now, because before we knew how we could associate our value type and our reference type. So when we're writing generic code, there was a pretty easy to understand way of associating those two together, right? If I add a reference to my value type, I have my reference type. Easy, depending on consonants. But we need to provide some kind of guarantees to generic code writers because they need to have this association sometimes. There is a way in the standard of associating different types with each other, common type, and that'll do things like the common type of int and double is double because both of them can be cast to double. That's fine, right? Unfortunately, it discards const, volatile, and reference, so it's not sufficient for what we need because we need to be much more specific in our iterators. So a common reference was introduced, and the common reference between two reference types is the minimally qualified reference type to which both types can bind. That's a dense sentence, but the important part, maybe read it again as I'm talking. The important thing to keep in mind is that we are binding a reference to another, this common reference type, okay? And we want to minimally qualify it. So if there are several candidates, let's have the least amount of qualifiers on it. So let's look at examples. I didn't come up with these examples, but and in the first example is pretty clear, right? If I want the common reference, what can I bind int ref and int const ref to? Int const ref. They both bind to that, okay? So if you're interested in how these things get calculated, I recommend checking out the papers. I just don't have the time for all of the particularities or really the understanding to explain all of it. But this is really what we're trying to solve with common reference. So how does this relate to iterators? For any valid iterator type, this is a fun one to say, the types reference, ref, and value type ref share a common reference, okay? These are the two types that we need to have one single type that they can both bind to, okay? That's really what we're trying to do here. And it might be clearer to you if I show it in this form. An iter's common reference type is the common reference between its reference type and a reference to its value type. This stuff is very dense, but we'll push through. Okay, so with this in mind, let's think again about that inner iterator where I had pairs of references as my reference type, right? For that, I need some kind of common reference. And I was using stood pair. So what I would like is for common reference to be defined like this, and it's not. So don't use this code. Don't expect that this is the case for stood pair. This is not the case. These are just a couple of examples, and this table is just from the perspective of an iterator that is supplying pairs of ints. These are the kinds of things that we would want to see. So this first example on this slide would be for that iterator, right? We have a pair of ints, and we want the common reference with that reference type, pair of int refs, okay? And so that should bind to pair of int refs. It's dense. So this is not how stood pair is defined, though, because that's not really generally the case. This is not really how we want this to work. According to Niebler, this is the main reason there's no zip view in C++20. We can't define common reference like this for all pairs, and there was some objection to the idea of adding something like common pair, which is a different but pair-like type that would do this the way we want for iterators. So to do this correctly, your iterator would basically need to have some iterator-specific pair-like type that customizes common reference, rather than using stood pair. Okay? So one of those types is common pair from range v3. Obviously, they've solved this problem. So this is what common reference looks like for common pair, and it even has common references with the normal stood pair. Okay, so if you want a type like this in your code, you can implement your own pair-like type and then specialize common reference, or you can just use the range v3 common pair. And the slide that I'm about to show you should encourage you not to customize common reference on your own until you have a lot of practice, because it's quite difficult. So how do you do this? How do I take common pair and define common reference to work that way? Well, this is all it takes. I slightly adapted this from the paper in that corner, P1035, Input Range Adapters, which was a proposal that included zip view but hasn't made it into the standard yet, as far as I know. You can see in common pair, we had to add member functions that allow casting to different pair types. This is an important step that I almost missed, so don't forget that piece. I'm a little bit confused about this line here because I'm not sure I've ever seen a const R value reference in the wild, and honestly, I couldn't find a test case to see where that was required, but I left it in because it's in the paper. So let's take a closer look at this one very quickly. The first thing you'll probably notice is that we don't specialize common reference, we specialize basic common reference, and we do it in a very weird way. This is a very clever implementation to allow for defining this type once without having to overload it for every combination of CVRef, because you can imagine that becomes a lot of combinations. So you define this for your types, and you are given some template, which is your qualifiers. So an instantiation of common reference with these types, T, some CVRef, U, CVRef, defers to basic common reference with these four parameters, T, U, Tqual, and Uqual, where Tqual is a unary alias template, such that Tqual of T evaluates to its CVRef, its original CVRef that you want. So this is what allows you to basically just define one of these, or two for the operators switched around. And you can use that Tqual thing in defining all of your dependent types. The second thing that you might notice is that this is using a parameter pack instead of just the two classes that our pair can hold. I copied it from a tuple implementation. So here's the version. It doesn't fit as well on the slide, but this is at least. So T1 is the type, the first type of our pair. T2 is the second type of our pair. And then there's a bunch of other stuff here. So unfortunately, I can't really get into the details of how this works, partially for time constraints, mostly because I haven't figured out an efficient way of explaining all of these combinations and teaching you how to do it. It gets very, very dense, and it's just kind of a lot of experimentation. That's all my ability has gotten me to. So
you know, things are starting to get interesting when you have 3 right angle brackets in a row. That's when things start to get interesting.
Yeah, I'm glad that you find that interesting. So that said, I do, here's a compiler explorer link with this implementation. If you just want to go there and start playing around with it, it has a bunch of test cases. Some of them I don't really understand. One of them, I think I found a bug in one of the compilers, but I'm not sure. They're all beta. None of them have finished the implementation of C++20, so we'll give them a break. But the paper that I took this example from had one of the few somewhat readable specializations of this that seems to exist anywhere on the internet. I cannot find very many places where basic common reference is actually specialized in some meaningful way. So check out that paper if you're curious about more of this. And then P0022 is the paper which introduced basic common reference. It didn't have a specialization of it, but it does introduce the concept and why it's necessary. So go to those if you need more information. So with that, we conclude our vector of bool aside, which ended up being most of the presentation. But let's get back to the solar system simulator and the all pairs view. So that was our outer iterator. And after that, we have just the very basic definition of like begin and end, and then the constructor. That's very straightforward. This deduction guide here, every view, as far as I can tell, has this. Basically, this is the decision of whether the input range needs to be wrapped in a view. So if we are given a vector, we need to wrap that in a stood views all. And if not, then we just use whatever view type. Because all of these views are expecting that they just get a view. Because I do this move in my constructor, and I expect that it should be moved, right? All right. So what about the piping operator? Because that's kind of the last piece of this puzzle that we haven't talked about yet. And kind of the most important in views. This is what gives us the composition that's so nice. This is the normal structure for the piping operator. So we just saw the all pairs view, and there's generally an unspecified type. The standard seems to be to use the FN suffix. This is the adapter type. So this is what people talk about when they're talking about adapters. But generally, they're talking about the instance of this adapter, which is publicly used. So the private type, the unspecified type, is what provides the composition and the operator pipe. And then the public adapter of it is what you use in pipelines. Things like transform, filter, those will create transform view and filter view. So this is the first pass at my adapter. You can see I have a basic concept to decide whether we can construct my view. And then we have the parentheses operator. And if you remember back to that early slide, the whole point of an adapter is to take a range and to produce a view. So that's all an adapter does. So that's all this does, really. Like I have a parentheses operator that takes a viewable range and produces an all pairs view wrapped around that range. And then I have some inline constexpr instance of that adapter. And that's what I would use in the pipeline. But I skipped over this line. This is a bad thing that I'm doing here. I'm inheriting from an MSVC type. So this is no longer platform independent. This cannot compile in GCC because they use something else. I don't actually know what they use, but this is bad. So this points at some of the problems with the piping operator. These are just a couple of them. So the piping operator and the adapter types aren't standardized. Implementations of these are incompatible with one another. There's nothing generic about any of them. And you can't use stood ranges with range v3 in some contexts. So that makes it pretty hard to use this feature because basically, if you're building up complex pipelines, you have to stick with one library. And if you're writing your own, you have to use that library. I didn't talk about the second point here because all pairs view doesn't require any additional arguments, like filter and transform require some operation that they need to run on each element, right? And you can build an adapter with that, but it doesn't have any input data. So you have like this half state. And these are just kind of a nightmare to maintain. So overall, it's just a hard feature to maintain. And without standardization, there are just too many different solutions to it. Of course, I gotta say, I'm not faulting anyone for this. We've seen a very tiny portion of a very small part of the STL in C++20. So I'm not surprised they couldn't solve all of the issues that exist. But these are some of the issues that exist. As for solutions, what do we do about this? Well, hopefully, my hope is that we can standardize the adapter pipeline kind of types, that composition of adapters. I don't know. I haven't tried to write a standard, a proposal for this, so I'm not sure how hard it is. I don't know why it wasn't standardized. So maybe it's a lot harder, but that would be my hope. Another option would be language support for a new operator. So this is P2011, which proposes a new pipeline rewrite operator for composing functions in the way that is shown in that box. So that's a possibility. I'm not sure that there are other solutions than these two. The issue really comes down to what was and was not standardized. So while there are plenty of ways to move forward, it really just comes down to library decision versus language decision. So also, quick note, You may know one of the authors of P2011 by their online name vector of bool. So clearly all of these problems are closely related. But in the meantime, we have a workaround. There is something you can do. I'm just not sure I recommend it. So here's some code I wrote, and these are the two modifications that I made to my adapter. You can this supported viewable range type is a concept that's basically just an OR of all of the viewable range types that I support. So there's one from std ranges, there's one from range v3. Those are incompatible and can't be done generically, really. So this is the viewable range concept from std ranges, and this enable view thing on the top right is a templatized bool constant that you can specialize to opt into your type being a view. And there's a different one for range v3 than for std ranges. So anyway, if you're curious about this borrowed range, by the way, there's a talk by Tristan Brindle from CPPCon 2020. If you didn't see that, I recommend checking that out. He goes into much greater detail on a wider variety of these. Okay, so these are all the concepts I had to define. Luckily, these two are the only ones that are like ORed together of multiple libraries. All the others just use those. So then let's take a quick look at generic pipeable. These concepts were taken straight from the MSVC STL pipeline. Pipeable into is useful. You know, left is pipeable into right if you can compose them in this way that we expect. Composable types is not actually an interesting concept. It's not relating left and right to each other in any way. It's just, I don't know. I just used what they were using. Jason looks like he wants to stare at this for a while longer, but I'm just going to skip ahead. So I need to handle a couple of cases. The first one is obvious. If my adapter receives a view, then I just return my view wrapped around the input data. That way I can just continue down the line with no problems. Note that this is the one case where I can usually use multiple libraries together. As long as there is input data in at the construction time, we're good. So in that last example, I have std views going into my view, going into ranges. We can do that because we have input data at construction time. That's an important part. So this is how I handle that case generically. This handles my adapter being an L value reference, which is generally the case that we use, but you know, we have to support R values as well. So keep in mind in both of these, there's no platform or library specific implementation. It's completely generic and there's no reason it shouldn't be. So you can see that the return type is the parentheses operator of the adapter, which is just returning a view wrapped around the view that was given to us. So this part is all very straightforward. This is actually quite stable and could be used in production because there's nothing platform specific. Unfortunately, I also have to handle building incomplete pipelines, which don't have source data. This is handled differently because we can't instantiate any of the view types until we know what actual data we're operating on. It's very easy to get tripped up on this because it requires an implementation specific pipeline type. Once that pipeline receives input data of some kind, it composes all of the views and produces a result. So this is the case that we can't use multiple libraries together. We have to stick with one for each pipeline. You can see it gets a lot more complicated. This is an example of another adapter piped into this one, and there's another version of this for this one piped into another adapter. And we can see, we can see that this is the pipeline factory, which is an unfortunate customization point. Basically, this needs to be specialized for every type, every library that you need to support. This is the MSVC specialization. So I have the generic pipeline factory. I specialize it for this particular component that MSVC uses in the pipeline. And I just have a create function that composes these things into the type that MSVC expects. This is the range v3 version. It uses a different type and a different way of composing them. I didn't test this one, but I don't know, it's probably fine. So then we can provide all of the overloads necessary for completeness. So, except up until 3 days ago, I didn't notice that I was missing an overload. So now, clearly this is a bad solution. So I'm sure there are more mistakes on this slide, but I didn't implement or test most of these. But let's take a quick look at this one. Why do we have to do all of these overloads instead of perfect forwarding? I'm not forwarding at all. So in this example, the input type is an L value of the pipeline type, and then I static cast it because it's using CRTP to the derived type. So I can't deduce the CVRef qualifiers there in the way that I want, or at least, yeah, I don't know. I have to be explicit. So I'm sure there are some tricks that could do this generically, and you would just have to write 2 of them, but I played around with it a little this afternoon and I couldn't quite figure it out. So this is how it is. So shortcomings of this implementation. This does nothing to solve piping one library into another for the intermediate types. This does not allow us to build an incomplete pipeline that uses multiple, but it helps with use your view in multiple libraries pipelines. So the second one, I think, is a shortcoming of the implementation. It's hard to opt into this thing. That whole OR of concepts is not a good implementation, but I can probably fix that. Overall, it's just not a clean solution. This is clearly tacked on to incomplete features. The fix needs to be with the features, not with this crazy third-party workaround code. So on that note, we took a look at all pairs view, and from all pairs view, I think that the main learning was that views are hard to write. They're not straightforward. There are a lot of edge cases that you have to think of, but they're very easy to use, and they're easy to test, to be honest. So C++20 is not ready for user-written views, but you could probably use range v3 until adapters are fixed. If you can pull in range v3, go for it. Their compose types are more stable. From vector of bool and the proxy reference types, we talked about proxies being unintuitive, but they are valid in C++20. So there are all these new iterators that you kind of have to plan for in your generic code. So keep these in mind, because if you start using proxy types with old generic code that didn't think about them, you'll get problems. So understand that these are part of the standard now and can exist, and might actually break some of your old code. So then we also talked about iterswap, itermove, and common reference. So customization points are incredibly easy to use in your generic code. Some of them are even easy to customize. And because the std-ranges algorithms use all of these customization points correctly and account for proxy reference types, make sure to always use those if you can. So thank you.
There's only so many people. Yeah, there we go. Some more people unmuting. Thank you, Jacob. Does anyone have any questions before I stop the recording? Anything that you think is interesting enough to be recorded here? That's a poor way to put that. Does anyone have any questions? Don't worry about if they're interesting or not.
Would you dare try this in production code?
No, no.
Thank you.
I should have included that in the conclusion slide. Don't write a view. C++20 is not ready, so don't use it in production. That's about it. If you have really strong control over your compiler and you're not worried about people using different versions or whatever, I don't know, maybe you could just inherit from the private, whatever your platform type is and be fine. But if you can use range v3, then you can inherit from the view closure thing, and that'll work nicely because that's pretty stable.
This feels like a shocking hole that there's no way for user-defined views.
Yep, that was a kind of a disappointing finding, to be honest.
The other thing that jumps out to me is like, I think I intellectually knew this because of the history of C++20 and ranges, but really realizing that most of the concepts in the standard library exist for ranges.
Yeah.
Well, and ranges wouldn't have existed without concepts also.
Right.
Oh, I forgot to mention one of the great things about customization points is that they're constrained with concepts at one place. So like with std ranges begin, there's a concept, you know, well, I guess you can't constrain it because that would be a circular dependency, but like you can constrain the customization point with concepts, and then the ADL stuff doesn't have to worry about concepts, which is nice. I forgot to mention that point.
Thank you very much, Jacob. That was awesome.